So this is actually going to be a fairly short talk, but just to tell you about a subject that is really a very, very important one, and that is how we validate OpenMM. So what does it mean to validate something? Well, basically it means we need to make sure that it works. And that means a few things. First of all, we need to make sure that it doesn't crash, because if you try to run a simulation and it crashes, that's generally not considered good behavior. But it's also very useful if it produces correct results, because if you think you've gotten a simulation but your results are all wrong, that's probably even worse. So we need to make sure that it runs and produces correct results. Now that's actually a pretty difficult thing to do, because we've got a really, really big test matrix for this program. Well, first of all, it's a big product. It has a lot of different features in it, and we need to make sure every one of those features works correctly. But then we also have to test under a lot of different environments. Well, first of all, we support 3 different operating systems, Linux, Mac, and Windows. So we've got to test on each one of those. But then we've also got 32 and 64-bit versions of those. And we have different OS versions, so we have to make sure it works on, Windows XP, Windows 7. Well, we haven't actually tested Windows 8. I'm sure we'll be getting into that soon. Different versions of Linux. There are many different versions of Mac. Then we've got the different types of hardware. We generally run on GPUs, but we have both NVIDIA and AMD GPUs. But that's not enough, because we have different generations of each one of those. So with NVIDIA, we've got, Fermi GPUs, Kepler GPUs, etc. Then we have to deal with different OpenCL implementations, because there's, NVIDIA has their implementation, AMD has theirs, Apple has theirs, Intel has theirs that we hope to support in the next release. And all of this creates this huge test matrix, and we need to try to test. We can't possibly test every single thing on every possible combination of all of these, but we try to come up with a representative sampling of them and test on as many reasonable configurations as we can. We have several distinct types of tests that we run. Just about all of them are automated in some way so that we can just run them automatically and see that they work. So the first type of tests we have are unit tests. These are relatively small tests that are designed to stress one particular feature or one particular piece of code fairly heavily and make sure that one feature is working correctly. Most of these are going to be very simple tests. So they will do things like create a system that consists of just a single harmonic bond, simulate it, and compare the behavior to the analytical solution and make sure that it's, matching to some reasonable tolerance. Some of them are a bit more complicated, like simulate a box of water at constant temperature and pressure, and then check that the average box volume is what you expect it to be for that temperature and pressure. Make sure that the average kinetic energy is what you expect it to be for that temperature. If you are compiling from source, you can actually run all the unit tests yourself. It's very easy. After building, you simply type make test and hit return, and it will go and run for a long time running all these tests. And it will print out every one of them and say whether it's passed or not. Actually, every one of these lines is really a test suite. Each one of them may contain multiple tests. And this will just run for a long time. If anything fails, you can then run them individually from the command line, and it will then generally print out a more detailed error message saying exactly what it is that failed. There's a small number of tests that are actually stochastic, like the one example I gave before, simulate a box of water, make sure that the average kinetic energy is what you expect it to be. It's a probability distribution, so we just check it against some reasonable tolerance, and most of the time we expect it to be there, but there's a small chance that every now and then it will fail. And when you run one of those from the command line, the error message will specifically say this test is stochastic and may occasionally fail. The next type of testing that we do is what we call system tests, and these are designed to test the library as a whole. So instead of focusing on just one specific feature, they try to do some big complicated test where if there's any error anywhere, that should cause this test to fail. So these are typically tests that involve realistic systems, proteins, DNA, RNA. We have tests that involve both implicit and explicit solvent, and they vary enormously in size, from tens of atoms to tens of thousands of atoms. And we have three types of system tests that we do, and I'll discuss each of them more specifically. So the first type are platform consistency tests, and these ones we simply compute the force on every atom for some system. We do it with the reference platform, we do it with some other platform, well, either CUDA or OpenCL, and then we just check, do the forces on every atom agree, does the total energy agree? And they should agree to some reasonably good tolerance, and you can find a whole table of these tests in the user manual if you're interested in seeing, exactly how precisely they agree. Next type of test is force-energy consistency. Of course, the force is the negative gradient of the energy, and so these tests are designed to check, is that really the case? And it's pretty easy to test that. You go to some configuration, you compute the force, and then you can go displace very slightly from that configuration and along some line, and compute the energy at a few points. From that, you create a finite difference approximation to the force, and you check that it actually agrees. So does it look like the force really is the negative gradient of the energy? And again, you can find a table in the manual that lists how accurately that really matches up for a bunch of systems. Then we have tests of integration, where for deterministic integrators, the thing we look for is whether energy is conserved, because if, with a determinist, or with a, basically an NVE simulation, you expect energy to be conserved. And so it takes a system, runs it for a while, and makes sure that the energy really isn't varying by more than some tolerance. And for stochastic integrators, so the NVT simulations, it just again checks the average kinetic energy and is it what you expect it to be given what temperature you've specified. And they do a few other things like these tests while it's running. It makes sure that all constraint distances remain within the tolerance of the expected distance. Final type of testing that we do is a direct comparison to other programs. So for the conventional force fields, we compare to GROMACS. For Amoeba, we compare to Tinker. And again, we simply go to some configuration, compute the force on every atom, compute the potential energy, and we do it with OpenMM, we do it with the other program, and we match them up and say, do they agree to within some reasonable tolerance? I believe that is all my slides. So just sort of a quick overview, but this is what we do to test OpenMM and make sure it's working correctly.